So now we're going to get into a discussion of the limiting reactant concept. So let's talk about what we mean by limiting reactant. Now, very often when a reaction is performed in order to produce a particular substance, we do not use necessarily the stoichiometric amounts proportionally of reactants to effect the reaction. So you might have one reactant or two reactants that may be more than necessary based on the calculations compared to the other reactant. So we have to make a distinction between what is known as the limiting reactant, which is the reactant which determines how much product would be obtained, and the excess reactants, which would be basically all the reactants. Now, they say here that it is called a limiting reactant because the amount of it is insufficient to react with the amounts of all the other reactants that are present, right? And as I said before, the limiting reactant limits the amount of product that can be formed. So to illustrate this, I want to use the example of bicycle construction. So let's say you're in the business of manufacturing bicycles, right? And in order to make 1 unit of a bicycle, we need the following. We need 2 wheels, we need a frame, and we need a pedal assembly. All right, so I'm simplifying it by writing it in the form of an equation. 2 wheels plus 1 frame plus 1 pedal assembly gives you 1 bicycle. All right, so that's the equation that we're going to use in order to find out how many bicycles we can make given the amounts of the different items. So let's say you have a situation where you have at your disposal 8 wheels, 4 frames, and 3 pedal assemblies. All right. Now the thing is, if we look at the manufacturing of bicycles based solely on the amount of wheels, we can conclude based on the formula that we just looked at that 8 wheels can be used to manufacture 4 bicycles, right? Because there's a 2-to-1 ratio between the wheels and the bicycle. Similarly, we can use 4 frames that are provided here to manufacture, again, 4 bicycles, all right? Based on the equation again. And then as far as the pedal assemblies are concerned, we can use 3 of them to make 3 bicycles, all right? So the question is, how many bicycles can we actually manufacture given that we have 8 wheels, 4 frames, and 3 pedal assemblies? Well, if you think about the equation, in order for you to use up all the 8 wheels, right, you're going to need 4 frames. So there's no problem there. But the thing is, we don't have enough pedal assemblies because in order for us to use up all the wheels and all the frames, we're going to need 4 pedal assemblies, but we have only 3. So therefore, the only thing we can do is use up all the 3 pedal assemblies. Those 3 pedal assemblies will use up 6 of the 8 wheels and 3 of the 4 frames. So therefore, the total amount of bicycles that will be manufactured would be 3 bicycles, right? So it is the number of pedal assemblies that is given here that will limit the number of bicycles that you can actually manufacture. And you'll notice over here, we have what is left over from those items that are not limiting, all right? We have 1 frame left over and 2 wheels left over, all right? So this is basically illustrating the whole limiting reactant concept using the manufacture of a bicycle. In this case, the limiting item, which would be analogous to the limiting reactant, would be the 3 pedal assemblies here, and the items that are in excess, which would be analogous to the excess reactants, would be the wheels and the frames. All right, so as stated here, the limiting part is the pedal assemblies. This is the part, therefore, that determines ultimately the number of bicycles that can be manufactured. All right, so that's basically just using this example to illustrate the limiting reactant concept. Okay, so let's get into an actual chemical reaction. So we're looking at this reaction, the reaction between hydrogen and chlorine to form hydrogen chloride. All right, so we're using some models here to represent the reaction. This represents the hydrogen molecule, this represents a chlorine molecule, and these are your hydrogen chloride molecules. All right, so let's say we start off with a situation where we have 4 molecules of chlorine, right, and we have 7 molecules of hydrogen. All right, So the question is, what would be the amount of product you expect to get? Now, in this case, it's a 1-to-1 ratio between the hydrogen and chlorine as described in this equation, right? So if we start off with the hydrogen and compare it to the chlorines, right, then you can see that the 4 molecules of chlorine will react with 4 molecules of hydrogen, and therefore you're going to have 3 molecules of hydrogen remaining, right? So therefore it is the molecules of chlorine that would be the limiting reactant, and therefore based on the stoichiometry of this equation, the 4 molecules of chlorine will produce 8 molecules of hydrogen chloride. All right, so therefore let me back up a bit here. So this is showing you the 8 molecules of hydrogen chloride: 1, 2, 3, 4, 5, 6, 7, 8. All right, and therefore you're still going to have some hydrogen remaining in excess. In fact, 3 molecules of hydrogen will remain in excess because 4 of the 7 molecules of hydrogen will react, and therefore we can conclude, so these are the 3 hydrogen molecules remaining, and therefore we can conclude that chlorine will be the limiting reactant in this particular reaction. All right, so how are we going to determine the limiting reactant in more complex situations? All right, so these are the steps that we're going to use to determine the limiting reactant in a reaction. The first step is that based on the balanced equation, you can calculate the amount of product in moles or grams as needed that is formed from each reactant. So basically what you're going to do is, based on the balanced equation and based on the amounts of each reactant that you start off with, you're going to determine the amount of product you expect to get. All right, then from there you can determine which reactant is limited. And how do you do that? As stated here, the reactant that gives the least calculated amount of product will be the limiting reactant. All right, any other reactant would be in excess. Okay, so when you do your calculations, starting from the given amount of each reactant, you calculate how much product you expect to get in each case. The one that produces the lower amount of product that you calculate would be the limiting reactant. And then you may be asked to determine the amount of the other reactant that would remain, the excess reactant. To calculate the amount of other reactant that would be required to react with the limiting reactant, you do the stoichiometric calculation between those 2 reactants, and then you can subtract that from the original amount of the excess reactant, and that would give you the amount of excess reactant. All right, so those are the 3 fundamental steps involved in basically limiting reactant problems, for lack of a better expression. All right, so we're going to go through a couple of examples. So the first example here, they gave you the balanced equation and they're asking how many moles of hydrogen chloride can be produced by reacting 4.0 moles of hydrogen and 3.5 moles of chlorine. And the question is asking also which reactant is the limiting reactant. So let me go to my pen function here. And let me start by saying, okay, so what you need to do, if you go through the steps as I outlined before, you're going to start with the number of moles of each reactant and determine how much product you expect to get. So I'm going to start with the 4.0 moles of H2 and determine, based on the balanced equation, the number of moles of HCl. Now, based on the balanced equation, there is a 2-to-1 mole ratio between the HCl and the Cl and the H2. So I'm going to write it like this in the conversion factor, and this gives 2.0 moles of HCl. All right. Then if I do a similar calculation, this time starting with 3.5 moles of H2, of Cl2, I'm sorry, and then I multiply by 2 moles of HCl above, 1 mole of Cl2 below, and according to, I'm sorry, this should be actually 8.0 moles of HCl, and this would be 7.0 moles of HCl. All right, so those are the amounts of HCl you expect to get based on the moles of each of these. And between these two, this value is lower, right? So therefore the answer is that this would be the moles of HCl you'd expect to get. And to answer the second question, which is which compound is the limiting reactant, and the answer is the chlorine would be the limiting reactant, because it is a chlorine that is based on the calculation would give the lower amount of product, when you compare to the other calculation. All right. So that's a relatively simple example of the limiting reactant concept. Now, the next example is a bit more complex because they did not give you, firstly, they did not give you the equation, right? So you have to figure that out. In fact, that should be the very first thing you should figure out. And then they also gave you masses of the reactants. So this one is a bit more complex. And then after that, you're asked to determine how much of the excess reactant. So that's another step that we have to look at. So let me start off by firstly figuring out what the balanced equation is. So the question says, how many grams of silver bromide can be formed when solutions containing magnesium bromide and silver nitrate are mixed together? So you have to identify the reactants. And in this case, the reactants would be silver nitrate. Okay, what's going on here? Silver nitrate and magnesium bromide. All right. And the question says that one of the products is silver bromide. So you should be able to figure out what the other product is, because basically the silver bromide results from the silver coming together with the bromide. So that means the other product would be the magnesium coming together with the nitrate. So therefore, MgNO3. And of course, you have to figure out what the formula for magnesium nitrate is. It is MgNO3 because nitrate has a -1 charge, magnesium has a +2 charge. So therefore, you're going to need 2 nitrate ions for every 1 magnesium to make sure that everything is balanced. The charges are balanced. Then, what you have to do is balance this equation, because this equation is actually unbalanced. So to balance this, we're going to need a 2 here, and we're going to need a 2 here. All right? So that's a balanced equation. So that's the first thing you have to do in order to solve this problem. Okay, so the next step is that we start with the 50.0 grams of magnesium bromide, and we have to figure out how much of the product you expect to get. So the product that we're trying to determine the mass of is the silver bromide. So the first step would be to convert from grams of magnesium bromide, this should be MgBr2, to moles. So you're going to have 1 mole of MgBr2, and below you're going to have the molar mass of magnesium bromide. So let me do that calculation here. MgBr2, and according to my calculation, this works out to be 184.11 grams. So I'm going to write that here. 184.11 grams of MgBr2. And then the next step is where we look at the mole ratio between the silver bromide and the magnesium bromide. We see it's a 2-to-1 mole ratio, so you're going to have 2 moles of AgBr and 1 mole of MgBr2, and I would work that out, all right, to get the moles of silver bromide. So let me do that on my calculator. So 50 divided by 184.11 equal times 2. And according to my calculation, this works out to be equal to 0. Let me do this again. I'm not sure if I did this correct. 50 divided by 184.11 times 2. Okay, so that is correct. Okay, so answer I got here is 0.543 moles of AgBr. All right. Then I'm going to do a similar exercise, but this time I'm starting with 100 grams, 100.0 grams of silver nitrate. I'm going to convert this to moles like I did in the previous line. The difference is that because I'm working with silver nitrate, the molar mass is going to be different. So Let me do the molar mass calculation here. Silver NO3. And according to my calculation, this works out to be equal to 169.87. 169.87 grams of AgNO3. And then I look at the mole ratio between the silver nitrate and the silver bromide, and you'll notice it's a 2 to 2 mole ratio, or 1 to 1, doesn't matter, same difference. So 2 moles of AgBr over 2 moles of AgNO3. All right, and then I work this out. So 100 divided by 169.87, and according to my calculation, this works out to be equal to 0.589. So I'm going to put 0.589 moles of AgBr. Okay, so those are the moles of those two products, or of the same product based on the two reactants, and you compare these two, and the one that is lower would be this one right here, the 0.543 moles of silver bromide. So therefore I would take that and say convert that to grams, basically 0.543 moles of AgBr. I would convert that to moles, so I would put 1 mole of AgBr below. Whoops. Br, and up here I'll put the molar mass, which is, let me do the calculation here, 187.77. So let me put that up here, 187.77 grams of AgBr. And when I do that, 0.543 times 187.77, according to my calculation, this works out to be equal to 102 grams of AgBr. So that would be the answer for the first part. All right. Okay. So on to the next step, and I'm going to need some more space to do the next step, because the next step, or the next question, is asking how many grams of the excess reactant remain unreacted. So what I'm going to do is get out of this here for the time being, and I'm going to open up another document, a new document. Let me take this out and take that out. Okay, so basically the next question is asking how many grams of the excess reactant remains, right? So we already identify the limiting reactant, believe it or not, because we know that this is a limiting, whoops, let me go back to this here. We already know that the silver, this is the amount of product you expect to get, the 0.543 moles. So that tells us that the magnesium bromide is the limiting reactant, right? Which means that the silver nitrate would be the excess reactant, all right? So what the question is asking is how much of the excess reactant remains. So in order for us to calculate the amount of excess reactant remains, what we need to do is to find out how much of the excess reactant reacted, right? Once we find out how much of the excess reactant reacted, then we can subtract that amount from the amount that was there from the beginning, and that will give us the amount of silver nitrate, the excess reactant remaining. So let me get out of this. Go to this here. And what I'm going to do is I'm going to start off with, let me see here, I'm going to start off with the amount of limiting reactant, which is the 500 milligrams of, let me do this here. I'm going to start off with the, I'm sorry, let me go here. Okay, and then let me open up the pen function here. Okay, so I'm going to start off with the 50 grams of magnesium bromide. Convert that to moles. So it was what, 1 mole up here of MgBr2. Over the molar mass, which I think we calculated already. Let me do it again. MgBr2, 184.11, 184.11 grams of MgBr2. And this time, we're going to look at the mole ratio between the magnesium bromide, which is the limiting reactant, and the silver nitrate, which is the excess reactant. And based on the coefficient, it's going to be a 2-to-1 ratio. We're going to have 1 mole of MgBr2 down here and 2 moles of AgNO3 above. All right, and then we're going to convert that moles of silver nitrate to grams, where we're going to have 1 mole of AgNO3 below, and above the molar mass of silver nitrate, which is, if I remember correctly, is 169.87. So let me do that up here. 169.87 grams of AgNO3. So I'm going to use my calculator to work this out. So 50 divided by 184.11 times 2 times 169.87, and that is equal to 92.3 grams of AgNO3. So this is the amount reacted. So the amount remaining is equal to the amount that you started off with, which is 100 grams. So you're going to have 100 grams, 100.0 grams here, minus the amount that reacted, which is 92.3 grams, and whatever that gives. So 100 minus 92.3, and according to my calculation, that works out to be equal to 7.7 grams. So this would represent the amount of the excess reactant, which is a silver nitrate, that will remain. All right, so that's another example of a limiting reactant type problem. Okay, so let me go back to this slide here. Okay, so in fact, that's a question we just answered. I should have used a space provided there, but that's fine. Okay, so we're going to stop here for today, and we're going to proceed to a discussion of reaction yield in the next video. Until next time.